The purpose of this video is to once again talk to you about the law of conservation of energy and to show using equations how mechanical energy can be conserved. So looking at this first slide here, law of conservation of energy, energy cannot be created nor destroyed. It can only be transformed from one form into another. I showed you some examples of energy transformations on the right hand side here. If we've got food energy is chemical potential energy, and we can convert that into, using various chemical processes, into kinetic energy, or the energy of motion. Radiant energy, energy from the sun, can be converted to chemical energy in the form of photosynthesis. Hopefully you heard about that last year in biology. Chemical energy, from that, for instance, of gasoline, can be converted into the energy of motion. So gasoline can combust to make the pistons of a car engine turn in order to move the car forward. And then finally, you've got electrical energy that can be transformed into thermal energy. So thinking about electricity flowing throughout a heater, the heater heats up the elements, and the elements will cause your room to get warmer. So those are all examples of energy transformations. So we can categorize energy into two classifications. The one we were dealing with in the energy skate park simulation was mechanical energy, when the ramp did not have friction. Mechanical energy can be all the kinetic and potential energy in a system combined together. And as you saw when you were looking through the Schoology assignment about potential energy, potential energy can be broken down into two different categories as well: gravitational potential energy and elastic potential energy. If we have friction in the system, like with the second energy skate park that you were playing with, then we can introduce thermal energy into the system, and we classify thermal energy as a form of non-mechanical energy. Non-mechanical means that it's energy that does not have to do work or does not have to cause an object to move. I also listed here a couple of other examples of non-mechanical energy, such as nuclear. That's non-mechanical. Nuclear energy can be present and not cause an object to move. And same with electrical energy. Let's focus primarily, though, on mechanical energy for the rest of this video. Obeying the law of conservation of energy, total mechanical energy in the system is the sum of all the potential energy and all the kinetic energy available. So we can symbolize that with the following equation. Capital M, capital E is the symbol for mechanical energy. KE again is the symbol for kinetic energy. PE is the symbol for potential energy. And mechanical energy in the system is equal to kinetic plus potential added together. I'd pause the video, make sure you have that equation written down into your notebooks. Again, obeying the law of conservation of mechanical energy, we know that the initial amount of mechanical energy in the system has to be equal to the final amount of mechanical energy available to the system. You saw that during the energy skate park in a frictionless system because the total energy never changed. Total energy never changed, although the kinetic energy and the potential energy kept on changing back and forth dependent upon the location of the skater on the ramp. So I can break down that equation a little bit further to say initial kinetic energy plus initial potential energy will equal final kinetic energy plus final potential energy. And if I substitute in the equations that we have already learned from kinetic energy and potential energy, more specifically gravitational potential energy, I can make the equation look like this. Where VI is initial velocity, where the first height is the first position an object is above the reference point. Where VF is the final velocity the object will have. And where H2 is the final height the object has above a reference point. Now, if I am starting from rest, if an object is at rest to begin with, the object has no initial velocity. So at rest, I can cancel out this term, and the initial gravitational potential energy of the object will equal the final kinetic energy of the object if the object also ends up at rest. So when you're looking at this equation here, if an object starts at rest and ends at rest, then you will be able to see that the initial gravitational potential energy will equal the final kinetic energy in the system. And remember, this is without friction or any other intervening energies in the system. Let's see how this equation works. However, before I do so, remind yourself to pause the video, write these equations down, and use them for the following example. So here's an example of a problem that you'll see in the law of conservation of mechanical energy. A small 10.0 gram ball is held to a slingshot that is stretched 6.0 centimeters. The spring constant is 2.0 times 10 to the second newtons per meter. I would like to find the final velocity of the ball as it leaves the slingshot. So, a couple things I'm going to do here. I'm going to remember to change my units into standard SI units. 10 grams needs to be converted to kilograms. So I'm going to right off the bat move that decimal 3 places over to the left and say this is the same as 0.0100 kilograms. Also, centimeters needs to be changed to meters. So this is going to be 0.060 meters. The spring constant that you saw when you did the potential energy assignment is defined as how much force is given in a spring per meter it's either compressed or stretched. And so the units for that one are just fine. So I want to find the velocity of the ball at the moment it leaves the slingshot. So I'm going to use the equation initial potential energy plus initial kinetic energy equals final potential energy plus final kinetic energy. And I will also know that before the ball left the slingshot, the ball was not moving, so all the energy contained in the system was potential. So I can immediately cancel kinetic energy initial out. As soon as the ball left the slingshot, all of the initial potential energy turned completely to final kinetic energy. No potential energy was left, so I can cancel out potential energy final. So I am left with PE initial equals KE final. So I'm dealing with an elastic potential energy because the ball is in a slingshot. So what I'm going to do here is write out 1/2 kx squared, and the final kinetic energy is going to be 1/2 mvf squared. I want to find, in this case, final velocity. I'm going to rearrange this equation to isolate final velocity. I see I can cancel out the halves on both sides. I can divide both sides by mass, and then I can finally square root, and this will leave me with final velocity is equal to the square root of the spring constant times how much it's stretched squared divided by the mass of the ball. So let's fill in what we know. Spring constant is 200 Newton meters.
If you're in the building, please come to the main office. Catherine Collins.
The amount the slingshot was stretched was 0.060 meters. And I want to make sure I square that. Divided by the mass of the ball, which is going to be 0.0100. All under the root. That's going to be the final velocity. Solving this out, we're going to take 200 times 0.06 squared, all divided by 0.01, and then square root. So the ball left the slingshot with a velocity of 8.5 meters per second. 2 sig figs because I've got 2 sig figs in my displacement of the slingshot. So this is a really good example of how to solve conservation of mechanical energy problems. Rewind the video anytime you need to, and this will allow you to do page 174, 1 through 4, and we're going to talk about that on Tuesday. Have a wonderful afternoon.